Hello students, I hope you're having a wonderful day. Today I would like to complete a practice problem solving for support forces. So we're going to sum the torques about point A, and I would like to complete a practice problem with you here. So let's go ahead and get started. Two students are holding up the ends of a 6.2 kilogram board that is 2.2 meters long. A 4.5 kilogram trophy sits on the board 0.85 meters from the right end of the board. So in this question, it's wanting us to complete four things. In part A, it wants us to draw a picture of the students, the board, and the trophy. In part B, it wants us to draw a free body diagram. And then in part C, it wants us to calculate each support force that the students are going to apply to the beam. And then in part D, it wants us to create a bar graph representing each support force. Okay? So in part A, we're just going to draw a simple picture of the students, the board, and the trophy. So what we can do is just draw this situation here. And here we have our static force. Here we have our board. And then we have the trophy sitting here. And if I'm going to dimension this, we know that the length of the board is 2.2 meters. And then the trophy sits 0.85 meters from the right end of the side of the board. Okay? So in part B, it wants us to draw a free body diagram. Now, you know that in a free body diagram, we are going to show all of the forces applied to the object, and in this case, that's going to be the beam. And then we're going to provide dimensions where all of these forces are applied. So we're just going to draw the beam here. In the middle of the beam, we are going to have the weight force of the beam acting. And like I said, in the very center of the beam here, okay? So the weight force of the beam, identified by F sub G, and I'm going to use the subscript of beam to help represent what we're calculating here. We're going to have the mass of the beam times the acceleration due to gravity. Now, the mass of the beam is 6.2 kilograms. The acceleration due to gravity is negative 9.8 meters per second squared. So we're going to take the product of those two values. So let's grab our calculator here. So I've got 6.2 times negative 9.8, and I get a negative 60.76 and a kilogram meter per second squared. This is in Newton. Now numerically, this value is negative, and this comes from the acceleration due to gravity vector pointing in a negative y direction. So this weight force, the weight force of the beam, this is also a vector, and this is pointing in a negative y direction. That's why we have this negative sign here. But on the free body diagram, we are not going to have a negative sign because our vector arrow is already showing the direction that the force is acting. And this is going to be in the negative y direction. So I'm going to label this here. Weight force of the beam is equal to a 60.76 newtons. And like I just mentioned, the vector arrow is pointing in a negative y direction. Next, we have the weight force of the trophy. Okay, so the weight force of the trophy, I'll just go ahead and draw my vector arrow here. So F sub G sub trophy. Once again, we need to calculate the weight force because this is going to be the force that the trophy is applying to the beam. So we're going to use the same setup for the equation. F sub G sub trophy is equal to the product of mass of the trophy and the acceleration due to gravity. So the mass of the trophy is 4.5 kilograms. Acceleration due to gravity is negative 9.8 meters per second squared. So once again, let's Calculate this, 4.5 times negative 9.8. I've got negative 44.1, and we have units of newtons. Once again, kilogram times meter per second squared is a newton. So 44.1. Now, we need to ask ourselves, how is our beam being supported? Well, we drew a very simple picture right over here, and we have two students holding up the board. And so, our board is in a state of equilibrium. So that means the sum of our forces in the y direction that are going down, we're going to have support forces equal in magnitude pushing back up on the beam. So we're going to have, since this is point A, we have support force A. I'm going to label this F sub A sub Y because this is a force in the y direction. And then over here, we're going to have support force B, also known as a reaction force. So F sub B sub Y, right here, okay? Now, the last thing that we need to do in our free body diagram is show some units. So we know that the length of the beam is 2.2 meters. So the weight force of the beam is acting at the beam center. So this is going to be half of 2.2 meters. That is 1.1 meters. So 1.1 meters. Next, we need to identify the location that the weight of the trophy is acting. Now we know that the beam is 2.2 meters, and we know that the trophy is resting 0.85 meters with respect to the right end of the beam. So our dimension is 1.35 meters. And the length of the beam is 2.2 meters. Okay? All right, so here is our free body diagram, okay? Now in part C it says calculate the force each student must apply to support the board and the trophy. So what we're going to do is we are going to sum the torques about point A. So you know that torque is equal to the applied force times the lever arm, okay? So we're going to start at point A, and we know that a counterclockwise rotation is positive, so let's go ahead and set up our coordinate system. Say counterclockwise is a positive rotation, and we are going to sum the torques about point A. Now, since the definition of torque is an applied force times the lever arm, so we're going to start at a position of 0 meters. Now, we're not going to have any torque at a position of 0 meters here, because let's think about this. I've got an applied force and times the lever arm. If the lever arm is zero, there is no torque applied at that point, okay? We have a force. You see we have a support force here, but we don't have any torque right there because our lever arm is 0. So we're going to start here. We're going to move in a positive x direction along the beam, and whenever we encounter a force, then we're going to calculate the torque at that point. So starting here, there's no torque applied to the beam. Moving in a positive x direction, nothing's going on. There's no force applied until, well, right here. We get to a position of 1.1 meters, okay? And the weight force of the beam is acting at a position of 1.1 meters, okay? So since we are summing torque about point A, what you need to do is think about this in 3 dimensions to where you can see the axis of rotation at point A, okay? Because you know torque is describing the tendency that a force can cause a rotation. So if you look at the direction of the arrow, this arrow is pointing down, and this is the axis of rotation here. this will cause a tendency to have a clockwise rotation. Well, according to our coordinate system right here, we've set up that a counterclockwise rotation is positive. So we are going to have a negative force value due to this causing a clockwise rotation. So I've got negative 60.76 newtons times the lever arm, and our dimension is 1.1 meters, plus, remember we're summing the torques about point A. So we're at the position of 1.1. We've recorded that. We're going to move on. We're moving in a positive x direction. The next force we have applied to our beam is the weight force of the trophy. It's 44.1 newtons, but it's going to once again cause a clockwise rotation. Okay, remember point A, if we could see in 3 dimensions, we would be able to see this axis of rotation right here. Okay, so clockwise rotation, I've got a negative 44.1 newtons times the lever arm. The lever arm is 1.35 meters plus, so we're right here moving in a positive x direction, nothing's going on, until we get to the end of the beam and we have support force right here, a reaction force. So F sub B sub Y. Now look at the direction of the vector arrow. It's pointing up. Here's our axis of rotation. So this will cause a counterclockwise rotation. So now we have a positive value for force. So F sub B sub Y times our lever arm. Well, in this case, our lever arm is the full length of the beam, 2.2 meters. And we're going to set all of this business equal to 0 because we're in a state of equilibrium here. Okay? Now, we're going to calculate the product of these two values. So we're calculating the torque here at this position. So I've got a negative 60.76 times 1.1 meters. I've got negative 66.836. Our units are going to be in Newton meters plus, I've got negative 44.1 times 1.35. I've got negative 59.535 Newton meters plus support force B, so F sub B sub Y times 2.2 meters, and we're setting all of this equal to 0. Now we're going to add these two values. I get negative 126.371. We have units of Newton meters plus F sub B sub Y times 2.2 meters is equal to 0. Okay? Now we're going to isolate support force B. First thing I'm going to do is add 126.371 Newton meters to both sides of the equal sign, and then I'm going to divide by 2.2 meters on both sides of the equal sign to isolate support force B. So what we have is F sub B sub Y is equal to, now remember we're adding this to both sides, so we're going to have a positive value. So 126.371 Newton meters divided by 2.2 meters. All right, so let's talk about the numerical value first. We've got a positive 57.441 right here. Our meters cancel. So unit-wise, we're just left with newtons. And so this is F sub B sub Y. Now I'm going to put a dotted box around this guy because we're going to need that, okay? So here we have support force B is 57.441 newtons. Let's go ahead and label that on our free body diagram, Okay, so we've got something that looks like that. Now, since our beam is in a state of equilibrium, we know that the total support force has to equal the total applied forces, but our vectors are pointing in opposite directions, okay? And since our beam is in a state of equilibrium, we can come up with an equation that says the sum of our applied forces plus the sum of our support forces must equal 0, since we're in a state of equilibrium, okay? Now, our applied forces are going to be the weight force of the beam plus the weight force of the trophy plus the sum of our support forces. Well, we have two support forces, so F sub A sub Y plus F sub B sub Y. And once again, we're setting this equal to 0 because we're in a state of equilibrium. So the weight force of the beam, we have 60.76 newtons. Now, we need to remember that weight force is a vector, so we must show direction when we're writing this down. You can see that we have a vector in the negative y direction here. So negative 60.76 newtons plus the weight force of the trophy right here, a negative 44.1 newtons plus support force A plus support force B. We're going to use our calculated value that we just calculated a few minutes ago, a positive 57.441 newtons. Set that equal to 0. All right, we're going to add these three values. So we have like units here, so we can add those. Okay, we get negative 47.419 newtons plus support force A. Set that equal to 0. We're going to isolate support force A by adding 47.419 newtons to both sides of the equal sign. And what we have is support force A is equal to 47.419 newtons. And I will put a box around that guy, okay? All right, so we have two positive values here, okay? So for A, we have 47.419 newtons. For B, 57.441, and that makes sense. Now, the support forces are not equal, but that makes sense because most of the weight, you see that the weight force of the trophy is closer to side B. So that means side B is going to support more weight. And so he is supporting more weight, 57.441 newtons compared to 47.419. Now, in part D, the problem asks us to create a graph representing the support forces supplied by both students. So we have a bar graph here. I can divide this up, A and B. So let's go ahead and label our x-axis. This is going to be support force. On the y-axis, we're going to have force, units of newtons. So force, newtons. And I'm just going to go up by a scale of 10 here. Okay, and for A, we have 47.419. So okay, so here we have that bar representing support force A. And B, so this is going to be the side that has a greater value because remember, the weight force of the trophy is closer to side B, so we're supporting more force. It's 57.441. Okay? And that graph is going to give us a good visual representation of our support forces. Okay? All right, I hope working through this problem has helped you today. As always, if you have any questions at all, you can send me an email, contact me over Canvas, or give me a call on my phone in the office. So, I hope you have a wonderful day.